guys, thanks for joining me. This is Mrs. Hammer. Today we're going to be learning about something called heating curves, which is a diagram that we study in chemistry that helps us do two things. It helps us better understand phase changes and what's really happening in a phase change or a temperature change, and also it helps us understand the energy associated with or the energy needed to undergo either a phase change or a chemical change. So we're going to get into it. We're going to be on page 5 of your notes. Alright, so here we are on page 5 of your notes, and again, this process that we're studying, or this diagram that we're studying, is called a heating curve, and essentially it's studying the math associated with phase changes, or in other words, how much energy is needed to cause something to undergo a phase change. So on page 5 you have a blank area, and you might want to draw this diagram that we have off to the side here. And as you can see, it's showing us how temperature is changing with time. So what you need to imagine is that you start with a pure solid at the beginning. So if you go back here to time equals 0, we have what it's labeled as ice, okay? So we have a very, very cold pure solid, and that's what we're starting with. And the diagram says time, but I also want you to add in that this is representing heat being added. So imagine we put that onto a hot plate, or we put a fire under it. So we're adding heat to it at a steady rate, okay? So what happens to that substance as we slowly add heat? Well, obviously, if you think about ice, you know that it's eventually going to melt and boil. But I want us to understand it in more detail, okay? So the first main idea is that when energy or heat is added to or removed from a substance, this graph could be flip-flopped, the following two things could happen. You might have a temperature change, and we see that on the graph by a sloped portion of the graph because the temperature, the y-axis, is changing, or we could have a phase change, and this is the flat portions of the graph. And it might seem kind of strange to you that as we continue to add heat, there are these portions of the graph where the temperature is not changing, but that is what we observe. So we need to better understand what's happening to the molecules. The energy is being added, and that energy is going into the molecules, but what is actually happening to the molecules? So that's what we're going to talk about. So if you need to pause it to finish drawing this diagram, go for it, and then continue on when you need to. Alright, so first off, what we need to understand is that we're going to use the term Q for the heat that we're being added, or the heat that we're adding in. And if we're adding heat, that's an endothermic change. We've gone over that earlier in the year. And Q for cooling or releasing energy is negative, and that's exothermic, okay? So a positive Q means that we're adding energy. A negative Q indicates that we are losing or releasing energy. So endothermic is a positive Q, exothermic is a negative Q. All right, so back on this diagram here. We have in detail written in your notes what exactly is going on, but let's really talk about what's happening to the molecules. So the first section of this graph that we see is labeled as pure ice. So we have this really, really, really cold ice, and we're saying that it's remaining pure ice even though we're adding heat, okay? And what's happening is in this portion of the graph, the temperature is changing from negative 20 Celsius to 0 Celsius, okay? So because the temperature is changing, okay, so we have a delta T, and temperature is measuring the motion of the molecules, okay? This positive change of the temperature means that the molecules are speeding up. Now, in a solid, all the molecules are doing is vibrating. So this simply means that the molecules are actually beginning to vibrate faster. But they're still locked into place, they're still a solid, and they're just moving faster, okay? Then we get to this flat portion, and we see that the temperature kind of flattens out at 0 Celsius, and it stays 0 Celsius for quite some time. So on this section of the graph, where it's remaining 0 Celsius, this is actually a phase change, okay? So the temperature is held constant, and it's held constant at 0 Celsius, which you might know as the freezing point or melting point of this substance. So for a while, the temperature is going to remain constant at 0 degrees Celsius. And in this case, because we're adding heat, it's going to melt. So what's happening to the molecules? Okay, the intermolecular forces, which we talked about last semester, the IMFs that are holding these molecules together, in this case the H2O, the IMFs are being broken. And we are switching from a solid, where the molecules are locked into place but vibrating, to a liquid, where the molecules actually have the freedom to slide past each other and they're no longer locked into place. So when we have this flattened out portion, it's not necessarily causing the molecules to have more kinetic energy. They're not moving faster. They're just moving in a different way. They're switching from the solid state locked into place to the liquid state where they have the freedom to slide past each other. So this flat part here where the temperature is constant indicates a phase change. All right, let's study the next section and think about what's going on. This next section is simply labeled as water. Of course, we could call it liquid. And we do have, again, a positive change in temperature. And increasing the temperature indicates that the molecules are speeding up, or molecules moving faster. Okay, so this entire time period, they're remaining in the liquid state. So the way that they're moving isn't changing. They're sliding past each other, but they're sliding past each other faster. And for water, it has the ability to do that all the way from 0 Celsius to 100 Celsius. And when it hits this point right here, things begin to change again. When we hit that point right there, the boiling process begins, and we have another phase change begin. So in this section right here, it's flat. Again, that represents a phase change. Okay, so it's not causing the molecules to move faster, it's causing them to move in a different way. So in the liquid state, they were sliding past each other. In the gaseous state, they're completely separated from each other. So again, the energy added is causing the IMFs to be broken or overcome. The IMFs that are holding those water molecules together slowly begin to break, and the water molecules now have the ability to completely separate from each other and turn into the gaseous state. So again, it takes a while for all the water molecules to change into that gaseous state, and it's kind of like a no man left behind situation. The temperature is not going to start to increase. Nobody gets to move faster. The temperature doesn't get to go up until all the molecules have been separated from each other and all of it has changed into steam here at the end, okay? And so we only have one section left, and you can probably guess what's happening. In this final section, we have a change in temperature. It's a positive change in temperature. So what that means is the molecules are moving faster as the temperature goes up. So they're not moving in a different way, they're just moving faster. They're completely separated from each other, they're bouncing off each other, they're bouncing off the walls. They're simply doing it faster and faster and faster as we increase the temperature. So that's how adding heat changes the molecules. There are certain times, like these, the sloped parts, where the temperature is changing. And that temperature changing means that the molecule speed is being affected. If it's a phase change, we're talking about IMFs being broken or formed if you're cooling down, okay? But IMFs are changing. All right, so now we're going to switch to page 6, and we're going to talk about how do we actually calculate how much energy is needed to do this, okay? So first off, in order to talk about how much energy is needed to heat or cool a substance, so we're talking about the delta T portions of the heating curves, or the sloped portion of the heating curve when the temperature is actually changing. We use this formula here that uses something called a specific heat, and specific heat is this variable lowercase c that's showing up right there in the formula, okay? So M is the mass, C is the specific heat, which is some constants. We'll see those listed in a minute. Specific heat. And delta T is the change in temperature. It's final minus initial. Final minus initial. Okay? Now, let's talk about what these numbers are. The specific heat for water depends on what state it's in. Is it solid ice, is it liquid water, or is it steam? Okay. Let's look at the value for the specific heat of liquid water. It's 4.18 joules, and then that's over grams, and it's over degrees Celsius. So we say joules per gram per degree Celsius. What this means is these are the units that show up in the other measurements. So if we look back at the formula here, okay, let me change my ink color to something that's better. If the specific heat unit is joules over grams and degrees Celsius, the joule is the unit of heat. So this has to be measured in joules. Gram is the unit of mass, and degrees Celsius is the unit for temperature, okay? So the reason this works is the grams and grams cancels out, and the Celsius cancels out, and so we have joules equals joules, okay? So when we're using the specific heats, we have to use these units: mass in grams, degrees Celsius for temperature, and joules is our Q value. Now, this only works for the sloped part of the line where the temperature was actually changing, okay? What do we do for the phase changes? We have different numbers to do this math, okay? The formula that we use looks different. The Q, or heat needed, equals the mole values multiplied by the delta H. Now, the delta H is the constant here, okay? On this one, the C was the constant. It's what you don't have to memorize, okay? In this one, the delta H is the constant, and they'll be given to you, okay? On our heating curve, we have two phase changes. We have, in this case, this would be melting, and in this case, it would be vaporization. So we have two different delta H's. It takes a different amount of energy to melt something than it does to vaporize something, and we'll talk about why that is in a second. But for this section here for melting, we use what's called the heat of fusion, okay? And so fusion is for either melting or freezing. If we're talking about the section for vaporization, we use what's called the latent heat of, wait for it, vaporization. Really exciting. And we use that for boiling if we're heating it, or condensing if we're cooling it, okay? So this one, the units are fairly easy to understand. If we look at what the values actually are for the heat of fusion and the heat of vaporization, it's kilojoules per mole, okay? So let's think about the heat of fusion, 6.01 kilojoules per mole. So this value right here, the unit is kilojoules per mole. Moles, guess what unit that is? Moles. And we have moles multiplied by kilojoules per mole. So the moles cancel out, and therefore our Q when we solve for it is kilojoules, okay? So that's one important thing that you do have to remember when you're looking at the when you're looking at the sloped part of the graph, the Q value that you get is in joules. When you're looking at the flat part of the graph, the phase change, the Q is in kilojoules. So you simply have to be careful and pay attention. At this point in your chemistry career, these numbers here are going to be given to you, okay? So it's not like you have to remember that this one's kilojoules and this one's joules. You simply have to observe that these are kilojoules and these are joules. All right, so we're gonna work through a practice problem here. And the first thing we need to do is kind of read the problem and see what it's asking us. So we see that it's asking how much energy, so I'm going to label that as Q, how much heat energy is needed to convert 153 grams of ice at negative 15 degrees Celsius to steam at 125 degrees Celsius. And it tells us the molar mass of water is 18.016 grams per mole. We already knew that, but that's useful information. First thing we need to do is analyze this whole situation here, okay? On a heating curve, we've got all these sections here. Where are we starting, where are we ending? Well, if we think about the fact that this melting, this phase change happens at 0 degrees Celsius, and this boiling phase change happens at 100 degrees Celsius, we are starting way down here below freezing, or melting, we should say, and we're ending way up here, okay? So we actually have 5 sections of calculations to do. The first section here for heating the solid. Second section is going to melt it into liquid. Then we're going to heat the liquid. Then we're going to vaporize the liquid. into a gas, and then we're going to heat the gas. So we actually have 5 separate calculations here. There's no shortcut, there's no way around it. You simply have to do the 5 calculations. The good news is after you do the first couple calculations, it's more like a marathon problem where you're doing the same thing over and over and again. It's not like each section is something new, okay? Now, one thing I want to point out is if we're starting at negative 15, this temperature change is positive 15 degrees Celsius. We're going up by 15. This temperature change is 100 degrees Celsius because it's going up from 0 to 100, and this temperature change is 25 because we're going from 100 up to 125 degrees Celsius. So that's just something to keep in mind. All right, if you want to draw this, feel free to pause, draw this graph, and then we're going to move on and do our calculations. All right, so our first section is we want to heat the ice. Okay, heating involves the temperature change, so the formula we're going to use is the Q equals mc delta T. So the mass that we have here is 153 grams. The specific heat, we have to use the specific heat of the ice, okay? If you remember back here, there's specific heat of ice, liquid, and steam, or solid, liquid, gas. So for our first one, we're using the 2.08 joules per gram per degree Celsius. 2.08 joules per gram per degree Celsius. And again, remember for that first section, to get us from negative 15 up to the melting point, that's a positive 15 degree temperature change, okay? Rewind it if you need to see that, a visual of that again. So Celsius cancels, grams cancels, our answer is going to be left in joules. Pause, round to the right sig figs, jot down your answer. Should get 4,800 joules, okay? The 15 limits us to 2 sig figs, so 4,800. All right, the next section of the graph was we actually needed to melt the substance, okay? Remember that melting happens at a constant temperature, so it's the formula that does not have a temperature change in it. So it's just Q equals the moles times the delta H, and this one's going to be the delta H of fusion because we're melting, and if we think back, fusion, latent heat of fusion was for melting or freezing, depending on if you're heating or cooling. So our mole value, well, if we have 153 grams, remember to convert to moles, we divide by the molar mass. We've done that many times this year. So this is our moles, okay? We're going to multiply the moles by the heat of fusion. Remember, for water, again, you don't have to memorize it, you just need to be able to use it, 6.01 kilojoules per mole. So 6.01 kilojoules per mole. So the moles cancel. So pause, calculate, write down your answer. Okay, we actually get 51.0, but we have to remember what the unit is, kilojoules, okay? In the end, I'm going to have to add all this heat up, so I want them in the same unit, so I'm going to write down 51,000 joules, okay? And I am going to make a note to myself, it's 3 sig figs, so I'm just going to underline that those 3 are significant, okay? All right, we have now melted the ice. Next, now we have all liquid, so now we want to heat the liquid. Again, heating implies a change in temperature, so we're going to go back to Q equals mc delta T. So again, here's where it's kind of a marathon. It's not something new. It's the same equation we used when we heated the ice. It's just a different portion of the graph. So the mass is still 153 grams. The specific heat has to be for liquid water. So looking back, for liquid water, it was 4.18 joules per gram per degree Celsius. And the temperature change, remember, for the liquid, we need to take it all the way from the melting point of 0 all the way up to the vaporization point of 100. So it's a positive 100 degrees Celsius temperature change, okay? So pause and multiply. You should get 64,000 joules needed and 3 sig figs there, okay? All right, we now have water at 100 degrees Celsius, so now we want to vaporize it, or I'm just going to write boil, okay, but it means the same thing as vaporize. Again, no temperature change here. This is the flat part of the graph. So Q equals moles times the delta H. This time it's the delta H of vaporization because we're vaporizing it. So the mole value, remember, moles are grams divided by molar mass, so 153 grams over the 18.016, that's moles. The vaporization value is 40.07. 40.7, that's kilojoules per mole. Okay, the moles cancels, so that unit cancels. Pause, write down your answer, and remember that it's in kilojoules. It's 345 kilojoules with 3 sig figs, so I'm going to write out 345,000 joules. Okay, and in a second we're going to talk about why it takes so much more energy to vaporize it than it did to melt it. We'll talk about that in a second. Last step, we're almost there. We've done 1, 2, 3, 4 of the 5 calculations. Finally, we need to heat the vapor or the gas that we've created. Heating is that final temperature change. So going back to Q equals mc delta T, the mass is still the same, 153 grams. The specific heat, we need it for the vapor phase, so the specific heat of steam, 1.84 joules per gram per degree Celsius. And we already at 100 degrees Celsius. Our final temperature is 125, so that's a positive 25 degree increase. So pause and calculate. We get 7,000 joules. Okay. All right. So I'm going to underline in red the 5 individual answers that we had. The first step took 4,800. The second step took 51,000. Then 64,000. Then 345,000. Then 7,000. Okay. So all of these steps were required to get us from our starting point of negative 15 to our ending point of 125. So our total is literally the total. You're going to add these 5 things that I've underlined and get the right number of sig figs as well. Okay, so take a moment to pause, calculate, and when you add all this up, we get 470,000 joules, or we could say 470 kilojoules. Means the same thing. Okay, so that is actually our final answer for this problem because it asked us how much energy is needed. This is how much energy is needed because it's how much is needed to get us from our starting point of really, really, really cold ice to our ending point of really, really, really hot vapor. All right. The last thing I want to mention is why does it take so much more energy to boil it than it did to vaporize it? Okay, so going back here, let's just glance at the numbers here. Why does it take more energy? Hang on. Why does it take so much more energy to vaporize it than it does to melt it? Okay, what we need to think about is the difference between what's happening in melting versus vaporization. Okay, so if we go to a new screen, if we're talking about melting, we're talking about molecules going from locked into place and really, really close together to not locked into place, but still really, really, really close together. Okay, so yes, it takes energy to break the IMFs that are holding them together in place, but it's really just enough energy to break them free. Okay, if we talk about vaporizing or vaporization, we're talking about going from that liquid state where they're pretty close together but free to move around to completely separated. Okay, and in order to get all that space in between them, in order to go from that intermolecular distance to this intermolecular distance, you have to put in a lot of energy to break that IMF and pull those molecules apart. So the delta H of fusion is always less than the delta H of vaporization because it takes more energy to vaporize and completely pull the molecules apart than it does to simply melt them and break them out of their locked-in position. All right, so if you can do a problem like this, you can do any heating curve problem. If you think about it, not all situations are going to require 5 calculations. If we had a problem that, let's say we had a problem that started us at room temperature, 20 degrees water. We're starting right here. And we want to boil it and heat up the vapor and maybe end up here at, let's say, 125 degrees Celsius. But we started at room temperature, let's say 25 degrees Celsius. Okay, so to get from point A to point B, how many sections does it involve? 1, 2, 3. Okay, so don't always make the assumption that you have to do all 5 calculations on a problem like this. If you're not starting with really, really, really cold solid and going all the way to really, really, really hot vapor, it may take less. Thank you for joining me. I hope you learned something. If you have any questions, please feel free to come see me in person, and I'll see you next time. Bye.